And I'm going to go ahead and annotate. So do you guys all see the screen? Yeah. So this is the example we were talking about. And we even derived what your congestion price should be. So this is the congestion price we derived the other day and the last week. CP should be equal to MC minus AC. Okay. But this is the marginal cost minus the average cost. Now, what I'll do is I'll give you a couple of average cost functions. So let's take a look at those. So let's look at this example here. So what we're talking about is that you are given the average cost functions for two different routes, and these are called ACA and ACB. And average cost functions are always defined based on how many users you're serving on the road, right? So number of users define what the average cost for each individual driver is going to be. So your average cost on route A is 1 plus 0.002 VA squared. And average cost on route B is 1.5 plus 0.001 VB squared. And this is, as you can see, that the travel time. So these things, ACA and ACB, you can think of this as in terms of travel time, or you can think of these in terms of the travel time as converted in the form of dollars. Okay? Now, this 1.0, if you remember from your last homework, this 1P, and then this is obviously, as you guys might remember from 321, this is obviously what we call the link performance function, right? You are defining as the cost, how the cost changes as new volume is added to the route. So these cost functions are link performance functions. Okay, so we used to call, when we're talking about traffic engineering or traffic assignment problem, we used to call them link performance function. And now, because we are doing some fancy economics, we call them cost functions. Okay, so it's the same thing. Now, if you look at the structure of this cost function, in the structure of this cost function, I have a fixed cost that I'm highlighting here, 1.0 for route A. That cost is fixed. It does not change based on how many drivers are on the road. Okay? It does not change based on how many drivers are on the road. So that's your 1.0. So you can think of this as this 1.0 can be thought of as what we call in traffic engineering or traffic assignment problem, free flow travel time. So that means that's the travel time you're going to incur, even if the whole road is empty. This is the time you're going to take on the road. So it could be 1 hour or whatever. And now, because we have converted the average cost units are in dollars, I've converted that into dollars. So it's $1 is the fixed cost of traveling on that load. And basically what we've done is we've taken that free flow travel time and converted into some sort of value for money or value for time. We've converted that time that you take, free flow travel time, into dollar amount. And let's say that comes out to be $1 in this example. So my question to you is, what is the fixed cost of traveling on route B? Take a second to respond via chat or via voice. What is the fixed cost of traveling on route B? Please don't leave me hanging here. Okay, I'm looking for more messages. Yeah, free flow travel time or fixed cost of traveling on route B. I have one response. Looking for a few more. We can move forward. Yep, 1.5 is exactly right. Thank you. So you can see that this is the fixed component of the route, 1.5 minutes or $1.5 rather. So what happens is that when both roads are empty, which route would be chosen by the initial users when both routes are empty? There's no VA is equal to 0 and VB is equal to 0. And let's say you are the first user making the decision whether to choose route A or route B. Which route do you choose? If you're making the decision, which route do you choose? Route A or route B when both routes are empty? So now the next question is, once you know the free flow travel time for route B, my next question is, if all initial travelers have a choice between route A and route B, they will obviously choose route A because it has a lower fixed cost or a lower cost when both routes are empty, only $1 versus $1.5 for route B. So everybody goes into route A. The next question becomes, when do drivers or users start to take route B at all? When do anybody, when does the first user gets on route B? What has to happen for that? So question we are trying to answer is that if all initial people take the lowest free flow travel time or lowest fixed cost route, which is route A in this case, so what will happen is that this VA value will keep rising. This VA value will keep rising, but it can only rise so much before the route B starts looking good to people. And let me propose a way to figure out what is that value for VA. Okay? So to me, this is what it would look like when 1 plus 0.0002 VA raised to power 2. Okay, so I'm just gonna, okay, VA raised to power 2 becomes equal to what? Now you should be able to tell me. What has to happen to the cost of route A, at which point route B becomes competitive? If I've given you this part of the equation, you should be able to tell me what goes on the right-hand side. I'll pause a second, give you some time. So VA has to rise to level 1.5 such that, because as VA becomes 1.5, now people will say, hey, both routes right now have equal travel time. Maybe I could minimize my travel time by going on route B. Okay, and now you can solve this equation. If you can get your calculators out and give me that value for VA, as that at what point 1 plus 0.002 VA squared becomes 1.5. So can you give me the value for VA here? That means VA will be equal to what? Because that's the step I'm missing in this calculation on this sheet. So if you could tell me using your calculators, what is that value for VA, at which point route B starts to become used? I'll give you a few minutes, a couple of minutes to work this out. Yes, so I do see some answers on the chat. That's pretty good. So VA has to be equal to 50, because at VA equal to 50, when there is 50 units of flow or trips per hour or whatever the units are, when there are 50 trips per hour, at that level of congestion on route A, route B starts to look good. So if somebody asks you solve this problem for user equilibrium, and they say that the total demand on both routes is only 40 units or 40 trips per hour, how would you, so my next question for you is, and I'm going to type that up also. So once you figured out VA equal to 50, so now question is, if total demand is 40 trips per hour, how would they distribute themselves on both routes? If the total demand is only 40 trips an hour, how would they distribute themselves on both routes? If total demand is only 40 trips an hour, VA plus VB total is only 40, how would they distribute themselves? See one response in chat. So the answer is yes. So that's right. All of that demand will just go to route A because route B hasn't been competitive, right? And you can directly see some problems there with that, right? I mean, it's fine, but it's probably not minimizing the total system travel time, maybe. Okay. So if the total demand is only 40 trips an hour, everybody just goes to route A, route B remains completely unused, right? But that's not the problem we are solving right now. But if the demand is more than 50, then, you know, some of the responses that you guys gave me earlier with regards to, okay, with regards to how the route B will become competitive and so forth. Yes, once route B becomes competitive, any demand level higher than that. So once the demand exceeds this 50 trips per hour, once the demand exceeds 50 trips per hour. So for example, if the demand total was 100 trips, the demand total was 100 trips like it is here, okay, then both routes will be used, and the equilibrium assignment would be when the drivers cannot minimize their travel time by switching routes. And for that to happen, the travel time on both routes would have to be equal. Okay? And then that way, you can solve this 1 plus 0.002 VA squared plus 1.5 0.001 VB squared. And then your VA plus VB is equal to 100. Now it's two equations, two unknown. And I think we solved this problem in 321, CE 321 class, but we solve it using little bit simpler equations, the traffic assignment problem. It's still two equations, two unknown, even though the equation itself is a little bit complicated with the squared. But what you will do is you will equate the travel cost on route A with travel cost on route B. So remember, this is ACA equal to ACB. And then also your second equation will be VA plus VB equal to 100. Okay. So then now you can solve this equation. How do you solve this equation, by the way? You plug in VB equal to 100 minus VA, and then you plug it in, into the first one and solve it. Raise your hand if you're not sure how do we solve these equations. I can go over that, but it's two equations, two unknown. Feel free to raise your hand and I can show you how to solve it. Or if you want to just indicate via chat, private message, even if one person responds like that, I'll be happy to go over that. You don't have to tell me who you are. I mean, you have to tell me who you are because you're going to be responding via chat, but you don't have to tell the whole class who you are. It's okay. But I don't mind going over this stuff. But if I don't have to, then I won't. Okay, so I'm going to assume that everybody is good with this and can solve this two equation, two unknown problem, even though the equation might be a little bit funky and quadratic here. Okay, so when you solve it, you get 58.1 and 41.9 as the split. So 58.1 trips will go to route A, 41.9 trips will go to route B. And if you want to figure out what's the average cost on both routes at that point, and that will be ACA at 58.1 will be equal to ACB at 41.9. And then both of your trips, both of your routes will be costing on average 1.68. Okay, 1.68. Now, if you want to figure out what's the total cost that the whole system is experiencing, it'll be TC total, which is 100 times 1.68, because total trips were 100 trips and everybody is experiencing 1.68 as their average cost. So your total system cost will be 100 times 1.68. Okay, so this is sort of your user equilibrium assignment that we used to do with simple linear equations in CE 321, but now we are repeating that with this a little bit more complicated link performance function or the cost function. Okay. Now the question is there a way to lower this cost? Is there a way to lower this network cost of $168 that's being spent by total system? Is there a way to lower this cost? Okay, so that's what we're trying to find out. Is there a way to lower this cost? So that's what we talked about in the last class, is that if somehow, instead of marginal cost on both routes to be equal, if you could somehow get to a point where, so I'm sorry, instead of average cost on both routes to be equal, if you could equate the marginal cost on both routes, at that point, we might be able to get to where the total system cost is even lower. Okay, so what we'll do is next is we derive the marginal cost of these. So what does the marginal cost look like? Okay, so if you know the average cost function, you should be able to derive the marginal cost functions as well. Okay, how do we derive the marginal cost function from the average cost function? Okay, remember we did a homework problem based on that. So once you know the average cost, you need to first figure out the total cost. So my first question becomes, what is the total cost in route A? So first question is, what is the total cost in route A? And that's what, sorry, that's the total cost on route A is given by ACA times VA. So you take the average cost equation, which is this right here, and then you multiply that by VA, and that becomes 1 times VA plus 0.002 VA raised to power 3. So you took the average cost function, you multiplied that by VA, and then you did the same thing to VB, ACB times VB. It's 1.5 VB plus 0.001 VB cube. Does that make sense? Questions? How am I deriving total cost function? Okay, no questions about total cost function. I want you to take a minute to write down the average, the marginal cost functions for both routes. What is the marginal cost function for route A? And what's the marginal cost function for route B? Pause the recording for a second. So this is what these functions look like for marginal cost. So you didn't do anything fancy. You just basically take the derivative of this total cost function for both routes. So with respect to VA for MCA, it becomes the derivative of this equation. So you take the derivative of this equation with respect to VA, and you end up with this one, the first one. And then if you take the derivative with respect to VB for this equation, you end up with MC of B. Okay. Now what you want to have happen, and we already derived yesterday, that if we somehow can charge the drivers congestion price that's equal to the difference between MCA and ACA, if you charge the drivers these values of tolls, these tolls will help nudge the drivers to a situation where, as they try to minimize their perceived cost, they will be distributing themselves as if they were distributing such that the marginal cost on both routes to be equal. Okay. Now, also, if you solve this problem where MCA is equal to MCB, so if you solve this problem as MCA equal to MCB. Okay. If you solve that problem, just like you solve the ACA equal to ACB problem, then you can derive that you can figure out what's going to be the total system cost in that scenario. Right? So if you take VA plus VB equal to 100, so that's your one equation. And then your other equation was 1 plus 0.006 VA squared equal to 1.5 plus 0.003 VB squared So if you solve these two equations, so remember, I'm basically doing MCA plus MCB with this equation, and my other equation will be VA plus VB 100. If I solve this equation, what you will find is that your total cost, whatever it is, it's going to be lower than this 168. It will come out to be lower than 168. Okay, you'll solve for VA and VB, and then you can plug in and figure out the total cost on route A and total cost on route B. And whatever that comes out to be, I guarantee you that it's going to be less than this 168 that you got before. Because right now, your marginal cost. Now, congestion pricing would not be necessary if the drivers on their own volition would take the route such that the marginal cost was equal on both routes. But the drivers won't do that, because obviously driving, as you know, it's a selfish activity in a lot of ways. And because it's a selfish activity, everybody's trying to minimize their own travel time. And I'm not even, this is not blaming anybody or anything. That's just the way things work. So because everybody tries to minimize their travel time, the total system travel time comes out to be just a little bit larger. Now, because drivers won't divide themselves on two routes such that the marginal costs were equal on both routes, you have to give them that nudge using the congestion pricing. So basically, by congestion pricing, you're raising the perceived cost such that that perceived cost becomes equal to the marginal cost. Okay, so that's why the congestion price that you want to charge on route A will be equal to MCA minus ACA. And then congestion price that you want to charge on route B would be MCB minus ACB. And in that scenario, the perceived cost of the drivers will be CPA plus ACA, which will be equal to their marginal cost. And same thing on route B, the perceived cost will be CPB plus ACB, which is equal to the marginal cost as well. So if you solve for that, if you do this MCA minus ACA equation, you end up with congestion price of 0.004 VA squared, and then at CPB equal to 0.002 VB squared. You see where I'm getting this from? I'm just subtracting the original ACA equation, or sorry, the MCA equation. I'm subtracting the original average cost equation, ACA equation, from the newly derived MCA equation. So what I'm doing is I'm just subtracting this equation MCA, so I'm taking that, and I'm taking the ACA equation that was given to me. So I'm subtracting MCA minus ACA. So this is what I end up here. So these gives me the toll amount that I should charge, and you can see this congestion price or the toll is dependent on the individual travel demand flow that exists on any given route. Okay, so now think about this. So this is how you think about how this application might work, right? So the way application would work is you'll have your user equilibrium principle going on, and then there would be 58.1 users on route A, 41.9 users on route B. So you'll start the toll based on these numbers. So pre-toll equilibrium, the toll on route A and route B, because remember, route A is more heavily used, route B is not as heavily used. So your toll will be based on these numbers. Okay, the toll will be based on these numbers. And remember, the average cost on route A right now with 58.1 users is 1.68, and route B is 41.1 users, but the average cost is same on both routes, right? It's still 1.68. So your write-up says the toll on link A and link B would be 1.35 and 0.35 respectively. What I want you to do is think about how these values are being derived. How do I know that that would be the initial toll that I should be charging? So what I'm imagining is that I have my user equilibrium established. I have 58.1 users on route A, 41.9 users on route B. Okay. My question to you is, it says at the original pre-toll equilibrium, before the institution of congestion pricing, the tolls on link A and link B are $1.35 and 35 cents respectively. How are these values being derived? I'll pause the video recording, and if you can think about that and let me know, please. So because you're starting from that user equilibrium situation, you know that on route A, you have 58.1 people. On route B, you have 41.9 people. So that's the volume you'll use. That's the traffic flow, demand flow you'll use to define your congestion price. And those congestion prices are going to be based on what gives you that marginal cost pricing. So MCA minus ACA gives you 0.004 VA squared. Okay. And then MCB minus ACB is 0.002 VB squared. So you just plug in 58.1 for VA and 41.9 for VB, and then this is the tolls that you're going to get. So you can verify it. So if you did 0.004 times 58.1 whole squared. Okay, so that will give you, oops, sorry, that will give you $1.35. Okay, so at this point, you're charging, is that clear, by the way? Any questions about this? Please let me know. There are questions. Now, if this is the total cost, no questions here, so that's good. So if this is the toll on route A. So at that point, your total cost, the initial on A would be 1.35 of toll plus 1.68 of travel time, right? Because you're paying $1.35 in toll and you're spending $1.68 on the travel time. So your total cost will be $3.03 on route B. And then similarly, you can derive the initial total cost on route B will be 0.35 plus 1.68, and that will give you 2.03. Okay, so what happens when you started this toll business is that your total cost on route A became 3.03, and total cost on route B became only 2.03. As a rational driver, what would you do? What do you do as a rational driver in this scenario faced with a toll like that? Yeah, good response. Yes, you will switch to route B. And that's exactly what's going to happen. And this will keep happening until what happens? So drivers, as a rational driver, I will switch to route B, and people will switch to route B. A lot of people will switch to route B because the total cost is much lower on route B at the beginning. And then the more volume or more demand will shift to route B. And what would that do? Yes. Drivers will keep switching until there are more drivers on route B. Until what happens though? Until the perceived cost, the toll amount plus the travel time cost on both routes become equal. And what is that? That is nothing but the marginal cost, right? That's how we figured out our toll. So we would like our perceived cost to be equal to marginal cost. And that's why we came up with these expressions for congestion price on route A and congestion price on route B. So the drivers will ultimately have no incentive to switch when the perceived cost on route A becomes equal to perceived cost on route B, which is nothing but the perceived cost, the way we've designed the toll, the perceived cost is nothing but the marginal cost. So perceived cost is nothing but the marginal cost. So then the new equilibrium will come when marginal cost is equal on both routes, because that's how we have designed our toll. So we can simply get, so the equation that will form then is MCA becomes equal to MCB. And in that scenario, MCA being equal to MCB would mean 1 plus 0.006 VA squared equal to 1.5 plus, I'm sorry, 1.5 plus 0.003. Missing 1 0 here. B. Okay. Does that make sense to everybody? Any questions about this? So your new equilibrium will come. Now what I want you to do is verify this equation. Take a few minutes to make sure that you could solve it. I know it's very similar to the last one, but I want to make sure that we're able to solve this thing. And you can also write this equation, same thing. I'm writing it as a marginal cost of route A being equal to route B, or you can write it as perceived cost on route A being equal to perceived cost on route B. Remember, that doesn't mean equal toll on both routes. It just means perceived cost on route A being equal to perceived cost on route B. So remember, PC and CP are two different things. CP is my congestion price. PC is my perceived cost. Perceived cost, the way I've designed my congestion price is that my perceived cost basically is equal to marginal cost of each route. All right. So let's take a couple of minutes to solve these two equations to a known issue. Okay. Let's take a few minutes. I'm going to go pause the recording here. So my total demand is still the same at 100 trips per hour. So my VA plus VB equal to 100 is the same equation. Okay, so I'm going to need my second equation is still the same, VA plus VB equal to 100. And then I can solve it the same way that I talked about. You plug in VB equal to 100 minus VA, and 100 minus VA goes here in place of VB. Okay, it goes in place of 100 minus VB. Or And then once you have one equation, it will be a quadratic, but you could solve it. And once you solve it, you get VA equal to 47.2 and VB equal to 52.8. Okay. Now, if you calculate the marginal cost on both routes, it will be 2.34. So you basically plug in these numbers into the marginal cost equation, and both trips will have equal marginal cost. You will also notice that the average cost on route A is only 145. The average cost on route B is 178. So what has happened is that because the trips went from route A to route B, route A's average travel time went down, and route B's average travel time went up. It used to be both. We used to be at 168, $1.68 when we were looking at the average cost of route A. When we were looking at user equilibrium, both routes had equal average costs. It used to be 168, but now average cost on route A has gone down because the trips have been diverted to route B. And then on route B, the cost is 178. It has gone up some. And you will notice that the toll prices will be 89 cents and 56 cents respectively. And where am I getting those from? I'm getting those from the numbers VA squared being 40, VA being 47.2. It's 0.0. So if you did 0.004 times VA squared, you will get congestion price on route A. And if you did 0.002 times VB squared right here and plugged in VB equal to 52.8, you will get. Now, if drivers could do this without the toll, if you exclude the toll, your total cost is the average cost of route A is $1.45. You multiply that by how many people are using route A, plus $1.78 on route B, the average cost, times how many people are using route B, and you add them up, your total system cost is 162. And remember, if you go up a little bit, the total system cost used to be, a total network travel cost used to be 168 before, and now it's only 162. As you can see, it's only 162. So what have you done? You've lowered down the cost by $6. Okay, so you reduce the cost by $6, or you can say, in terms of percentage terms, 6 divided by 168, which is about 3.5%. So we've brought down the total system travel cost by about 3.5%, slightly more than 3.5%, almost 3.6%. So that's the role of congestion pricing, is that by instituting the toll that accounts for how many drivers are using your route, you can actually divert some trips on other routes, or in some cases you might basically discourage some people from traveling, and that's a good thing. And that's what the congestion pricing idea is about. So this is your, and then if there are total 100 trips, you're making 6 cents per trip of economic benefit. Okay. So perceived cost from link A goes from 168 to 145 per trip. The average cost on link B rises to 168 to 178. If you want to figure out the toll revenue in the steady state, you can figure out the toll revenue. It used to be 89 cents per person and 47.2 trips there, plus 56 cents per person times 58. And that's about $70, $71.50 at about 72 cents per trip. Okay. And now if you want to refund all the toll back to everybody, if you refund that 72 cents, the total toll revenue, 72 cents per trip that you made, and you refund it to everybody, the link A would pay at 17 cents net toll, and link B will receive a subsidy of 16 cents per trip. Okay. So that, the total perceived cost will be down to that marginal cost. Like, if you refunded all the toll money, then the total perceived cost of total trip will be $1.62. Okay. So this is sort of the theoretical example of the congestion pricing. Does this overall make sense? Anything that you're not clear about?